thank you very much, and thank you for the introduction. So I will explain, I guess, the title during the presentation, so you will understand what is a species niche clustering pattern later on. So from a perspective of a workshop here, so it's a work that have been done with Matilda Haraldsson. She's currently a postdoc with her own grant paid by Formas, which is a Swedish grant. We are both on the ecologist, biologist side for the workshop. We are both community ecologists, and we are interested in coexistence of species. And it's still work in progress, so I'm happy to have feedbacks on that. Okay, so let's start by a very ecology type of slide. One interest, I think, in ecology and ecological community in particular is to try to understand species coexistence, and especially how many species can coexist in ecosystems. Here you have an example of phytoplankton species in an aquatic system, and they can be very, very species rich. And in fact, these species occur in systems where you have very few different types of limiting resources. And one big question is to try to understand how so many species can coexist. So you can see that you have diverse number with different shapes here in the photo. So this has been a long-standing question in ecology. And in fact, one of the classical and seminal model on that question address the impact of competition for resources and species coexistence. So it's a model that is quite old, developed by MacArthur and Levins. As you can see, it's from the classical Lotka-Volterra competition model in the equations here, and I will develop a bit this model because it will be a basis for the following of the talk here. So we saw this model already this morning, so it's based on ODE, differential equations. You have one equation per species. And what I will be interested here is alpha HI, which is a competition coefficient between species. And in this model, here, MacArthur and Levins were interested in understanding how dissimilar or similar species need to be to coexist. And here, what I mean by similarity, so you're interested in the characteristics of a species, the species niche here, and it's defined in the model by its ability to consume resources. And the assumptions in the model here is that you have a function that the resources are implicit, but you consider that species can be described by their utilization, use of the different resources. And this use is described in this model by a Gaussian function. And you have mu I here, which is in fact characterized the preference, the center of a preference of a species here. And you have sigma, which is called generally niche width for the ecologist. So you have a niche position and the niche width that will follow on in the talk here. And when you're interested in competition here, and in this model, in fact, competition is just the overlap of these two functions of resources. And this overlap that is calculated here, you can see that if you have the same niche width here, the overlap and so the competition coefficients depends basically on the distance between the two species on the niche axis. So the more similar, the more competition between they use the same resources, and the less similar, then the less competition because they use some sort of different resources. Okay, so that's very basic. That's the model that will be throughout the talk here. So in this paper and in other papers, basically the main results on that is that in fact you can show that species can coexist only the distance between the two, the d, is large enough relative to the niche width. And there are numbers of papers following this model, but generally the main result is that you need to have some sort of limiting similarity to allow coexistence, stable coexistence of a species. Okay. If you are too similar, then you can't coexist, one excludes the other. So that's, well, kind of a classical result. And it has been also quite influential and studied also in fieldworks and empirical studies, where we have quite some interest and some idea that species that have different types of traits related to their resource use, here you have different species of finches. In fact, when you have competition, you expect that species, their traits will be in some ways quite dissimilar because of this competition. Okay, so that's part of the story here, but in fact, the work I will present here is based on a paper a bit more recent than MacArthur and Levin's, where in fact they used the MacArthur and Levin's model, but they did numerical simulations. And for these numerical simulations, so you have only competition still, okay? And in these simulations, species can have some sort of different carrying capacities, but not too much. They have the same growth rate R here. The competition coefficients depend on their positions on the niche U, and you have sigma, which is still the niche width here. And if you have a large number of species, the simulation, from what I remember, was with 200 species, what you find is that you have a long-term transient case where you have here the abundance of the different of the species depending on their position on the niche. And you can see that you have these clusters, these groups of very similar species that coexist for quite a long time until at the end you have only one species per group. So you have a limiting similarity of MacArthur and Levin's I was talking about at the start, but you have groups of very similar species that coexist for quite a long time on the transient dynamics. And what they show in this paper is that, in fact, they also add evolutionary dynamics, and you can also have a bit of immigration. And in fact, these clusters, these groups that you have on the niche axis, in fact, can be persistent for a long time when you add evolution or immigration or other types of processes. So it's something quite interesting for ecologists in a way that to coexist, it means that you need either to be quite similar or quite different. It's not only a matter of being very different from the others. Very similar species can also coexist for quite some time. Yes?
Is it exactly the same coefficient as in the original MacArthur and Levin's model? This alpha J, I can't recognize it.
In fact, it's just expressed a bit differently, but it's the same. There are some models which are a bit different, where the function here differs a bit. But here, in fact, it's exactly the same. Which was just written differently in the paper. Okay. So this sort of clustering pattern, as I will call them later on, in fact, they've been also found in data. So you have examples of 3 studies here, where when, of course, here it's not an abstract niche axis, but you use some traits of a species, some characteristics of a species as a surrogate of their resource use or as of their niche. And what they found is that for example, for phytoplankton species or aquatic beetles, you can have these types of groups of species which are a bit similar, and with groups which are between groups which are quite dissimilar. And in rainforests with height of the trees or wood densities, you can also find this type of clustering patterns, which seems to differ from random expectations. Okay. So So that was for the empirical part, and for the modeling part, in the recent years, there have been a number of models. Here, it's quite a good paper where they compared different types of models and looked in which case they had this kind of clustering patterns that emerged for different types of competition models. So it seems that transiently, you can quite often get this kind of groups of species that coexist for quite a while. With Matilda, we were quite interested in these patterns. And what is interesting here is that, in fact, most of the models have considered so far competition. And our question was to extend this work to including prey-predator interactions in the study. Okay, so that's what I'm going to talk about, basically. What about trophic interactions, and how do they affect these results? So there are a number of theoretical works showing that predation and trophic interactions definitely matter for species coexistence. I will just list a few here. For example, there is some work showing that predation can promote coexistence. Even for species that compete for only one resources, you can have coexistence if the predators are specialists. Okay, so it depends on whether predators can eat many prey or not. Another interesting aspect with predation is that, in fact, when two prey share a common predator, you have an indirect interactions between the two prey. So you have a negative indirect interactions between the two. So it's called apparent competition in ecology, meaning that you will have these negative indirect effects between the two prey as they share the same predators. So meaning that predation can also limit coexistence when you have this sharing of predators. And there are also a number of papers showing that the effects of competition for resources and predation depend on different characteristics of the ecosystem, such as the productivity, the amount of resources in the ecosystem. So here I just give an example of a paper where the model was a set of different prey species sharing the same predator and the same resources. And here the prey are ordered with NA here, which is the prey that is the best competitor for the resource, but also the more sensitive to the predator. So the predator eats more of this resource. And said, here is the less competitive for the resource, but also the most resistant for predator. And what they show in this paper is that if you have at low productivity, you tend to have one or two species that coexist, and it's species that resist more for predators, but which are more competitive for the resource. And the model shows that at high productivity, you have the opposite. You still have one or two species coexisting, but it's the species that are the more resistant to predation that persists. Okay, so that's some of the classical results on that, and I present them because they will be important for later. Okay, so I arrive here for the main questions of this talk. So basically, what we planned to do was to extend the work of Schaeffer and Van Ness to add predation to the model. And in particular, we were interested in understanding how the prey niche width and also the predator niche width affect these clustering patterns. Do they occur and how they depend on them? And because ecosystem productivity also matters for the relative importance of competition and predation, we also studied the impact of ecosystem productivity. And there will be two parts in this talk. In fact, it's in the reverse order of how we started the work. We started the work with numerical simulations that I will present at the end. And we found out that there were some papers with analytical work on this topic. So we did, well, I mean, analytical, we are ecologists, so please, yeah, it will be simple here, but We also did a bit of analytical work to extend the work that was existing on Lotka-Volterra competition model to predator-prey model. Okay, so let's start with the analytical part here. And basically, it's based on the work of Ford and collaborators. There's two papers, in fact, 2009 and 2010, where what he did in his paper, basically it's the model I presented earlier. So it's Lotka-Volterra model with competition coefficients which depend on the difference between the position of the two species on the niche axis. And you have here the niche width, which is the same for all the species. What they assume here is that you have n species, and they are distributed evenly on the niche axis, and the niche axis is circular, meaning that if you have 0, 1, and -1 species, in fact, mu n equal mu, mu I equal mu n minus I. Okay, so the niche axis is circular, and it's quite important for the derivation here. So the position of the species are evenly distributed on the niche axis, and what he showed is that in this case you can calculate in general the eigenvalues at equilibrium and the corresponding eigenvectors, and in that case here it just numerical showing the values, but here it's the dominant eigenvalue of a system. It's always real here. Here is the number of species n in the system, and here it's the niche with sigma. And okay, it's not a very beautiful graph, but what you can see is that it's always unstable. It's the equilibrium for which you have all the densities positive. Okay, all the species are there. And so it's always unstable, but the components of the eigenvector, which is corresponding to the dominant eigenvalue, has a particular shape, I guess, as a function of niche position. You can see that it has this periodic shape here. And in fact, that corresponds exactly to the clusters you get when you do the numerical simulations. So, okay, so it's a way, in a way, to do a bit of analytical work on that. And in fact, this can be understood from the assumptions of the model here, and especially from the distribution of species on the circular niche axis, because in this case, the Jacobian matrix is a circulant matrix, and then you can directly calculate for any n, for any number of species, the different eigenvalues of a system, the eigenvector of a system, and then the number of clusters depend on which eigenvalue is the largest one, basically. Okay, and what is quite interesting, in fact, is that when you look at the AGI here, they strongly depend on the number of species, but also on the niche width. And in fact, you, in a way, find back a bit the results of MacArthur, but in a cluster type of way, meaning that if you have a low niche width, small sigma n, then you will tend to have many little clusters, because this corresponds to you have many little waves in the components of the dominant eigenvector, and as you increase sigma n, then you have less and less clusters, and you have at the end species which are very dissimilar after the transient dynamics. Okay. So it's a way of estimating the number of clusters depending on the parameters. So what we did from that, we decided to try to extend a bit this work to a Lotka-Volterra predator-prey model. And to do so, we used a model that was used by Chesson and Kwong because it's a model, in fact, that has been used to try to understand coexistence between 2 or 3 species, depending on their overlap for resources and for predators. So it fitted quite well. And basically, for the analysis of this model, so I have to go a bit slower, sorry. So you have 3 trophic levels. You have resources, the equations here, where you can see that the resources, they don't compete. You just have intra-specific competition here. You have intermediate species N, which will be a focal species here, which consume the resources and are consumed by the predator. And the predators here, they have, in fact, this term here is negative, meaning that they need the prey to sustain themselves. And again, you don't model competition there, but you have an intra-specific competition term. Okay, so we followed the analysis of Chesson and Kwong, which is quite basic, meaning that we assume that we have fast dynamics of the resources and the predators. And in that case, you can simplify, well, approximate and simplify the system by focusing on the intermediate species here. And you find back Lotka-Volterra competition model, where the parameters, the growth, intrinsic growth rate here, and the interaction parameters here depend also on the resources and on the predator terms. Okay. And in particular, this is what is described by Chesson and Kwong in other terms. The overall competition beta here is determined by both overlap of consumption of resources, and here it's the consumption rates of the different resources, and it depends also on overlap regarding predation. Okay, so. And you can see also that there is an additional term here that is called by Chesson and Kwong relative predation intensity, meaning that this overall competition depends both on whether the N species have a similar consumption of resources, but as well they have similar predators, and the relative strength of these two depends on the ratio of the growth and the intraspecific competition of the resources and the predator. Okay, so that's that's the main result here. So what we did then from this simplification, we can follow the same type of approach than Fort and collaborators. It's a Lotka-Volterra competition model. We consider that we have N species. They are distributed evenly along the circular niche axis. And here we assume that the competition for resources, depending on the difference between the niche positions of the 2 N species, and the overlap in predators, depended also on this same difference, but here we have 2 niche widths, one which characterizes the niche width for competition for resources, and the other that characterizes the niche width of predator, basically. Okay. Okay. So again, well, circular and Jacobian, the terms here are a bit more complicated, but we can see that that depends on sigma n and sigma p, and on the ratio of attack rates and intraspecific competition of resources and predators, and which means that the eigenvalues, dominant eigenvalues, and corresponding eigenvector depends both on this niche width of prey, niche width of a predator, and on this relative predation intensity. So what is interesting from maybe more ecological point of view is that it means that in fact the number of cluster is going to be determined both by the niche width for competition and the niche width for predation. And that the relative importance of the two depends really of growth rates of the resources and growth rates of the predator. So here it's just a graphical way, numerical applications here, where we can predict the number of clusters for these different cases. When relative predation intensity is quite low, then it's more the niche width for the prey that determines the number of clusters. And as the niche width increases, you have less clusters than when it's low. And if you have a high predation intensity here, it's the opposite. It's mostly the niche width of the predators, whether they are more or less generalist, that is going to determine the number of clusters. Okay, at least from what we expect with these simplifications. Okay, it might not be that surprising, but basically it extends a bit the work by Chesson and Kwong, which highlighted that competition in predation, in fact, in these models can be just viewed symmetrically. And we can show that both can derive niche clustering patterns. And also, it depends on different parameters, the relative importance of predation and competition. And in particular, it will depend on the productivity of the systems, which here depends on the growth rates of the resources. Okay, so let's go for numerical simulations. In fact, because we had started numerical simulations before going to the analytical work, in fact, numerical simulations are based on a different model. And in fact, what we did, we extended the model of Schaeffer and Van Ness from their paper in 2006 by adding a predator level. Okay. So the model, we just add a predator level. We have the same number of predators than the number of a prey. Okay, if you have n prey, you have n predator species in this model. You have a competition part, which is basically the same as in MacArthur and Levin, and the same as in Schaeffer and Van Ness model, which depends on the position of n of a species of a prey on their niche axis. And for the predator attack rates here, we have in fact two niche axes in our model, one niche axis for the predators and one niche axis for the prey. And basically the attack rate here depends on the difference between the value of the prey on its niche axis and the prey values on their niche axis, which is also quite classical way to model these things. And we have again the same as before, the niche width of a competition and the niche width of a predation here, which basically in the case of predation characterize whether the predators are specialized on a small set of prey or generalist. Okay. So for the simulations, we followed exactly the same approach than Schaeffer and Van Ness. The different species were positioned randomly on the niche axis. And we had a large number of species, 200 prey and 200 predators, and we simulate the dynamics of a species over time. And basically, we look at whether we observe clusters. And I didn't say, in fact, for finding clusters, there is some algorithm to detect cluster and detect whether it's it differs from random, basically. So we have an algorithm here for cluster detections. Okay. So here it's an example of an output of a model for one simulation. Here you have always the niche axis of a prey, the niche axis of a predator, and you can see that from this simulation, which is quite characteristic of what we got, you find clusters for both prey and predators. And what is quite interesting is that you have a general correlation between the number of clusters in the prey and in the predator, but it's not necessarily exactly the same. Okay, you see that they are not exactly symmetrical here. You don't have exactly the same shapes. And when you compare from the same set of parameters, but with only competition between the preys, you can see that, well, you can have quite different clusters. So definitely predation can affect the number of clusters that we found, which is as expected from the analytical work. From the simulation work that we did, of course, it depends, I guess, on the parameters, but with a set of parameters we have here, we compared the case with predator-prey model with only prey system with competition. And however, we don't have strong differences in the number of clusters, and we can see that they can stay for quite a long time. But the main difference between the two was that, in fact, in the predator-prey system, clusters seemed less transient than for the competition case, at least in our simulations. Here it's the number of species per cluster. So when you have only one species per cluster, I mean, yeah, there's no really groups. And you can see that over time, you have a strong decrease of richness per cluster for the competition case than for the predator-prey case. So it sort of stays longer in the predator-prey model here. I'm not sure it would work with other sets of parameters, but at least with all the parameters we used, it was this. And let's go back to the same type of results that the one we did with analytical work. So we were interested in understanding how the niche width of the prey, the niche width of the predator, and the system productivity, which is here measured as the prey carrying capacity, affect the number of clusters in the system. And here, well, at low K, you have low productivity. At high K, you have high productivity. Here it's for the prey community. Oh, I forgot. Here it's sigma n, and here it's sigma p. And in fact, we find results which are quite in agreement with analytical expectation from the other model. That at low productivity, it's mainly the sigma n, the niche width of a prey, that determines the number of clusters. And you have less clusters when sigma n is high, when you have higher niche width for the competition. While it is the opposite at high productivity, where it's mostly sigma p, the niche width of a predator, that determines the number of clusters in the simulations, with lower number of clusters in the prey community when you have high generalism of the predator. If you look at the predator part, it's a bit more complicated. You seem to have this tendency of having a niche width for the prey, which is more important at low carrying capacity and low productivity, while it is more the reverse at high carrying capacity. But you can see that both matter, in fact, at low carrying capacity, at least, yeah, in these simulations. Okay. So that's perfect. I'm nearly finished. So it's still ongoing work. Well, at least from the analysis we did, it's quite interesting to see that there are some agreement, at least partially, between the numerical results and the analytical predictions here. Our results show mainly that predation and competition both derive this potential niche clustering pattern that we found. So it might be something quite general in this type of models. And the relative contribution of predation and competition depends on the productivity of the system. And in fact, what is quite interesting is that it's quite similar to other types of models, the model of labeled I presented earlier, where at low productivity, it's mostly the competition that drives the pattern, while at high productivity, it's more the relation with predation that drives the pattern. Well, in addition to developing a bit more the work I presented, I think one far but interesting perspectives would be to move from this bipartite or tripartite network to more general food webs models. And in fact, I think there's quite some interest in in ecology on that, because food web models are already based on niche traits quite strongly. Here you have an example of a model where species are ordered by their body mass, and in fact their feeding range depends on the body mass, etc. So I think one thing I would like to do is to move, to this type of models and see if we have again this type of clustering patterns that emerge. Okay, and thank you for your attention.
So, do we have any questions? Yes.
Thank you. Due to the special form of your competition rates, e to the minus something positive, they are all less than 1, and the strongest competitor for one species is always itself.
Yes.
Would it make sense to somehow authorize strongest competitors that are not the same species?
And I think it would affect a lot of the results. In fact, there are a number of papers showing that how this kind of assumptions on the shape of competitions strongly, in fact, determines this. Maybe not necessarily the clustering patterns, partly. In fact, it tends to be driven when you have more extreme competition for itself compared to others. And when it's the reverse, you don't have this type of clustering patterns. So I think for sure it would.
Yeah, hello. Thank you for this really interesting talk. I was wondering, predator-prey interactions can often lead to oscillations. I was wondering if that's something that you saw in your simulations, or how that would, sustained oscillations, or how that would affect the question of clustering.
Sorry, I didn't listen to the start, but you were asking about oscillations in the dynamics, in the predator-prey dynamics. That's what you said?
Yeah, I wonder if you saw oscillations, yes, or if other models have seen them, and how that affects clustering.
In fact, I didn't show videos here, but in some of the cases for simulations, we had oscillations, and you had like sort of little waves of clusters that were appearing. Yeah. So you can have oscillations indeed in some cases, but we didn't go more than that, just than observing it.
Thank you.
Yeah, just one question. So you said that depending on whether they are generalists or specialists, the number of clusters will change. But does that change also the biomass in those clusters? Because we expect generalists. You will have less clusters for generalists, but
it does. And we looked at it, but I don't remember. But definitely biomass and abundance depends on sigma and sigma p and the different parameters. And also what I didn't discuss at all, and we need to look at more on that, but you have sometimes extinctions. And I guess that can affect quite also the results. Yeah, abundance definitely matter and change.
Okay. And just about the question of cluster. So when you have oscillation or stuff that is moving, does the abundance or the number of clusters are always is stationary, or it's also changing when there is this periodicity?
That's a good question. Because we just observed it, so I can't say in general if it changes. An impression, but yeah, I had the impression the number of clusters stayed the same. They were just moving. On the niche axis, it's just the oscillations of a species that make the impression that you have this moving. Well, you have a moving cluster, but they just keep the same number.
Maybe a quick one for me. So I was wondering, how stable are these clusters themselves? Like, you have the same number of clusters, but are the species you have in a cluster, do they stay the same, or do the distances between stay the same? So is there some kind of stability within clusters?
So I think the species stay the same, but some get extinct at some point. So it's just that you have, at the start, you have more species and then the number decreases, but they stay the same, well, except if it's oscillate, yeah. But the distance definitely stays the same, at least from what we saw. But we would need to measure it, I think, more, yeah.